what I did in the last lecture is basically define some models. Models where the spins are interacting with each other, and many different kinds of models we define. So from this lecture is going to be to start to work out what effect this interaction has. So earlier we had done non-interacting electrons, non-interacting spins, etc. Now we put this interaction in, and this certainly affects the thermodynamic properties of the system. So what we would like to find out is how the properties of the system are affected by these interactions, and particularly some methods to take care of these interactions, to include these interactions in the calculation. And that would be quite difficult in general. So I mean, you must be aware of the fact that many body problem is much more difficult to do rather than single particle problems. When you study gases, for example, ideal gas is very easy. So that's something that everything can be worked out explicitly, and you know whatever is supposed to know about that. But as soon as you put in some interactions, then the problem becomes much more difficult. And in most cases, the exact solution is not possible. So there, the issue that comes into focus is how one can develop approximation methods to take into account the effects of interactions in any system of particles, system of spins, and things like that. So here, of course, we are concentrating on spin systems. So I will start at the simple level by again some examples where things can be worked out explicitly and you have an exact solution. But in most physically interesting cases, will not have exact solution, and then one has to develop various approximation methods to take into account the effects of interactions. So the models that I wrote down in the last lecture, perhaps the simplest model was the Ising model, where you have variables at each side. You can look at it as the z component of a spin or something like that. Can take only two values, +1 and -1, and then there is an interaction between the nearest neighbor spins, which could be positive or negative. And depending on whether it's positive or negative, we'll have different kinds of behavior. In some cases we'll have ferromagnetic behavior, some cases anti-ferromagnetic. So we'll try to understand some of these things. Before going into that, let me just do a little bit of an aside. Although in this whole course is about magnetism, some of the models that we'll see in this model, in this course, will have applications that still much beyond magnetism. So just to keep in mind that these models are not explicitly for magnetism, but in general, these models sometimes help in understanding properties of some other systems also. So just to give you a simple 5-minute illustration or 10-minute illustration of how these models can be used to study other systems, let me just again look at the Ising model. Ising model is something that I had defined earlier. You have a Hamiltonian, which is minus some coupling constant, and let's say you have only nearest neighbor interactions, ij with a bracket like that. I mean that we are dealing with a lattice system, so the spins are sitting on a lattice, and this is just a sum over nearest neighbor pairs of lattice sides. And then you have sigma I, sigma j, and each sigma I can take two values, +1 or -1. So this is the simplest Ising model. That you have the spin variables which can take only two values, +1 or -1, and then nearest neighbor interactions. And when the two spins have the same sign of sigma, then you have negative energy, and when they have the two spins of opposite signs, then you have positive energy. So this favors the alignment of the space. And this for j is big. Assume that j is bigger than 0. So this gives you ferromagnetic. So this is the Ising model in the context of spins. I'll just give you one simple example where the same model describes the physics of something which is little different. And this system that I'll just going to talk about is binary alloy. Binary alloy, what do we mean by that? You have again, let's say, a crystal lattice, and some sites are occupied by one kind of atoms, A, and some other sites are occupied by a different kind of atom. So, to take a picture, so I mean, I'll just draw basically circles or crosses. Circles represent A type of particle and crosses represent B type of particle. And one says that, you have some configuration like that, and there will be some energy associated with this configuration. And the energy will depend on whether two of these occupied sites are of A type, or two of them are of B type, or one is A and one is B. Right? So, basically, circles are A and crosses are B.
What do you mean by A and B sublattices?
Not sublattices, these are two different kinds of particles.
Up and down.
At this point, we're just looking at just the copper magnetism. Two different kinds of atoms or ions which are sitting on the lattice. Okay, so the problem is now no longer magnetism problem, it's called a binary alloy. And the lattice and each lattice site can be either occupied by A type particle or B type particle. And the energy, of course, will depend on which nearest pairs are of what kind. Right?
Can this be mapped onto the ISO model?
That's what I'm trying to show. That this problem, it doesn't have anything to do with magnetism. This problem becomes exactly similar to the Ising model. And mapping or arises because of the fact that you have this variable at each site tells us about whether it's A type particle or B type particle. And this is two-state variable. Ising model also is a two-state variable. It can be +1 or -1. So it's fairly easy to map one problem into the other problem. So if I just write one or two lines that will make the analogy very clear. In this case, the Hamiltonian, again, some over here pairs, I assume that energy depends only on what is nearest neighbor. It doesn't matter whether the second neighbor is A or second neighbor is B or C, whatever. Energy depends only on the first neighbor. So you will have some potential BAA. So for each lattice site, I define a variable sigma I. Sigma I is equal to it can take two values, and one corresponds to A particle, corresponds to B particle. This is the auxiliary variable. I'm just defining each site can be either A particle and B particle. I'm defining a new variable which I call sigma I. And if I see a particle, then I call the sigma I to be equal to +1. If I see a B particle, I call it sigma I to be -1. Sorry for that. So what does it say? If sigma I is equal to 1 and sigma j is equal to 1, that basically means both of them are A particles, and then there will be a energy which is VAA. Similarly, we will have VAB. AB will come with two terms. When one of them is A and the other one is B. So delta sigma I 1 delta sigma j -1 plus delta sigma I -1 delta sigma j 1. This is just a product symbol that I'm sure all of you are familiar with. This is equal to this 1 or 0 depending on whether these two are the same or not. Yeah? And then there will be dBB delta sigma A sigma I minus 1 delta sigma J minus 1 bracket. So this is just saying that if two nearest neighbor sites are occupied by A, which corresponds to the corresponding sigma variables, will be equal to 1. Then there is one value. If one is A and the other is B, then you have another value. Both of them equal to B, then you get another value. And this can be converted into that form fairly easily. If I now write this conical deltas, delta sigma I 1 is 1 plus sigma I divided by 2, delta sigma I minus 1, 1 minus. This is trivial sigma. Sigma I is equal to plus 1, then this gives you 1, and sigma I is equal to minus 1, this gives you 0, and this is the other way. So I write this delta function simply in terms of sigma I and sigma j basically, and then expand this thing out. You will get basically a term like that. There will in general be also a term which is linear in this sequence, because each of these, as you can see here, each of them will be 1 plus or 1 minus whatever. So there will be, if you look at cross terms, there will be terms which involving just the sigmas. And the term that involves just the sigmas is like a magnetic field. So I mean, in general, if I write the Hamiltonian here, more general Hamiltonian, which is minus h sum over I sigma I. This is the general Hamiltonian for the Gaussian model. There is the interaction term, and then there is the external field term that we have looked at earlier. So then it's just 2 lines of algebra to convert this form to that form. I mean, write all of this conical deltas in terms of this 1 plus and 1 minus sigma, just do the algebra. We will get a bilinear term, which will be something like this. So J and H will now be determined in terms of this potentials, some combination of the potentials. So this you can do yourself. But the point is, whenever you have a situation where at each site you have a variable that can take 2 values, you can always convert that into an Ising model, because one value we associate with sigma equals plus 1, other value we associate sigma equals minus 1, and then just by doing this, you should be able to convert one problem onto the other. So, there are many such problems. Instead of binary alloys, one looks at mixture of 2 different liquids. There again, the same formulation applies, that binary liquids are also very similar to Ising models. If you have a liquid gas kind of system, then one can map that to a lattice gas, which is again an Ising model. Lattice gas mapping just says that you again have a lattice like that, and each site can be occupied or not. The number of objects or particles that you have sitting on the lattice is smaller than the number of lattice sites you have. So the question is that which lattice sites get occupied, and when it is occupied, you can call it sigma equals plus 1. When it is unoccupied, you can call it sigma equals minus 1. And again, that problem will be mapped onto exactly what I have written there, where the coupling constant and the magnetic field, these things are determined by terms of this potential that you have. So I think model is important. I just want to the digression, just to tell you that I think model is important, not just because some problems in magnetism require solving the Ising model, but there are physical problems which are not in magnetism, which also can be mapped onto the Ising model. And so if you understand the Ising model, then many different things can be understood. There is one more thing that I need to point out when I am looking at this kind of analogy. There is a little bit of difference between the standard Ising model in magnetism and this model. Can anybody see the difference? I mean, Hamiltonian is very similar. There is nothing, no difference with Hamiltonian, but there is something which is different.
The spins can convert from up to down, but A and B atoms cannot. A cannot.
A cannot convert to B, but 2AB can be interchanged. If you have AB, then it can become BA. So exchanges are possible, but flips are not possible.
The Ising model we can get a net, everything becomes plus 1, but here the number of plus 1 and minus 1
would be fixed. In some sense, here, if you look at actual A's and B's, you have put only certain number of A's there and certain number of B's there. So, and that number remains fixed. And the difference between the number of A and number of B is like a magnetization. A is spin up, B is spin down. So, if equal number of A's and B's are there, magnetization is equal to 0. If they are unequal, there will be some finite magnetization. But that magnetization doesn't change with the function of time. As when you're doing the ensemble average, the ensemble that we have to use to average this quantity is basically a different ensemble, whereas it's a fixed magnetization. And whereas in the other case, in this case, it's a fixed magnetic field ensemble, in the sense that like magnetic field at particular temperature, number of up spins and down spins will be determined by that. As either the magnetic field or the temperature, these numbers will change. So the ensemble that one uses to describe this kind of problems and that kind of problems, they are different, but they are related to each other. Just like when you are looking at gas, one can think in terms of constant pressure ensemble or constant volume ensemble, or you can look at constant chemical potential ensemble, constant number ensemble. So
yeah, it also mentioned the lattice gas.
Yeah, lattice gas also, I mean, the number of particles that you put on the lattice, that is fixed. They cannot just go away. So, I mean, there is sort of like a fixed number of particles ensemble, but you can put in a chemical potential there, and then you can work in the ensemble where numbers fluctuate and so on. Both is possible. Okay, so this is just an aside. But it is useful to keep in mind that some of the things that you learn in studying the magnetism, they actually have very wide applicability. In the sense that when here, for example, I have this Ising model I just talked about. Now we have XY model. XY model where the spins are confined in the XY plane in the spin space. But I think I had mentioned this briefly. This model also is used to describe phase transitions in superconductors, superfluids, some liquid crystals where the same thing applies. So these are actually applicability of these models is much more general than just in magnetism, but in this present context, we are of course looking at these models arising from interaction of magnetic space. So that's that. Okay, so now amplification has to be turned down. Okay, then I sort of, no, it's not complicated at all. Now we discuss number.
It's okay.
Hello? Hello?
Yeah.
It's okay?
Yes.
Good. So now let's try to sort of solve some of these problems involving Ising models. The first problem that I would like to look at is Ising model in one dimension. And we'll find out that for that model, one can get exact results. One can solve the problem exactly. One can get results. Our going to be important. In particular, given a model, what one wants to understand often is whether the model has any phase transition. So, ferromagnetic Ising model, when we talk about, then one expects that because of this tendency of the spins to line up, at low temperatures, one will have a ferromagnetic state where majority of the spins are pointing in the same direction. But we'll see that the answer to that question is not that simple, in the sense that every system will not exhibit a phase transition. And here, the dimensionality of the problem becomes important. Whether the Ising spins that we are looking at, they are sitting on a one-dimensional lattice or a two-dimensional lattice, three-dimensional lattice, it matters very much. And so those things are also important. Those things I'll try to sort of illustrate by working out this simple case of Ising model in one dimension. How many of you seen this derivation? Okay, there are still a substantial number who have not. So let me just spend a little bit of time on that, and as I said, it will also illustrate certain important concepts that will be applicable to other systems also. So now I am looking at Ising model, but in 1D Ising model. So I have basically a line, one dimension, some lattice size. Like that. And each lattice side you have, here you have sigma 1, and here you have sigma 2, etc., etc. And let's say I have n such lattice sides, which is sigma n. And for the time being, at least, we assume that this is an open-ended system. That there is nothing on this side, and there is nothing on that side. It's free boundary conditions. And you have the same interaction, G times sigma 1, sigma 2, plus J times sigma 2, sigma 3, plus all the way up to J times sigma n minus 1. This is basically the Hamilton with the overall minus sign. It doesn't matter actually, non-dimension, whether putting the minus sign or not, it doesn't matter. And so what we want to do is that now this system is there at some fixed temperature T, and we want to calculate various thermodynamic properties. What is the internal energy, what is the magnetization, if there is any possibility of having a non-zero spontaneous magnetization, ferromagnetic quarter enhancements. So to do that, you have to again do this usual thing. You have to look at the partition function Z, this trace e to the minus beta times this Hamiltonian. And traces basically means that this is sum over sigma 1 equal to plus minus 1, sigma 2 equals plus minus 1 all the way up to sigma n equals plus minus 1. These are the variables of your problem. Each sigma can take two values, plus 1 or minus 1. So when I say trace, it's a simple notation. It says that I have to sum over all possible values of these variables that determine what the energy is going to be. Right? So what is this one here? Trace all the way to the beta j times sigma n minus 1. Yes? There is a minus sign here, so I have this minus sign goes with that. Beta is what? Beta is 1 over kVt. So this is what calculation that I have to do. And my claim is that this calculation can be done in 2 lines. Thus people see why this calculation is easy to do. You could have seen it, of course, they know, but others. So I mean, just a few lines of algebra. So exponential beta j times sigma 1 over sigma 2, this quantity, sigma 1, sigma 2 itself can take only two values, plus 1 or minus 1. Right? So it's very easy to see that this quantity can be written as cosine hyperbolic beta j plus sigma 1, sigma 2 sine hyperbolic. Is that obvious to everybody? Sigma 1, sigma 2 is this quantity that has two different values, plus 1 or minus 1. If it is plus 1, then the positive exponential comes into the picture. So this is what. I'm just writing out the explicit hyperbolic cosine and hyperbolic sine. Now, if sigma 1, sigma 2 is plus 1, then these two add together and these two will cancel each other. So we just get e to the beta j. If sigma 1, sigma 2 is negative, then the first term will cancel out and you will get the second term, which is e to the minus beta j, which is exactly what you have over there. So this is just a different way of writing things. But this helps because we'll see how it helps. So this I can also write as, take the hyperbolic out. Right? Just some trivial algebraic manipulations. So each term I can write like that. Yes? So each term will give you a factor of cosine hyperbolic beta j, and then we have a product of terms like this. So just do that. Trace, and then so how many terms are there when total number of sites is n? How many bonds are there? N minus 1. So that's simple. And then you have the trace. And then you have 1 plus tangent beta j sigma 1 sigma 2. Way, and then you have 1 plus again times beta j sigma n minus 1 right? So for each bond we have a term like this, and we have n minus 1 bond, so we have product of terms that look like that. And then I have to sum over all sigmas, taking two values, plus 1 or minus 1. Right? So, can you just look at it and tell me what this case is going to be? So there are two terms in each of these brackets. So if I multiply these things out, there will be some terms, the first term will be all 1. There will be a term like you will take this for this bond, 1 for this bond, and so on and so forth. And the point is, since I am summing over sigma to be plus or minus 1, we cannot have any term that involves only one spin. Because any term that has only one spin, let's say sigma 1, sum over sigma 1 to be plus or minus 1, that will give me 0. So essentially, when we expand this thing out and then do the trace, every spin, term that will give you non-zero value is 1, for which every spin appears twice. Because it appears twice basically means that sigma square is equal to 1, because sigma can take only 2 values, plus or minus 1. So then that will survive when you sum over sigma equals plus 1 or minus 1. So is that clear to you? So that is the basic point here. So let's just write out a few things here. First term, second term here. So here, the first term is where you take 1 here. 1. Second term will be when I take this and then 1 everywhere else. So that will give me times beta j sigma 1 sigma 2. But when I do this trace basically means that each sigma can take 2 values plus or minus 1. So whenever I see 1 sigma, it can take either plus 1 or minus 1, which is sum over both these two things, and that will give me 0. Yeah? And I'm just writing 2 terms, but it is for you to convince yourself that all the terms that I'm going to generate here, where any time I see this times function, that will give me 0. Because, for example, I can take term that involves 2 of these times. So let's say 1 from here, not 1 from here, times from here, times from there, that will be sigma 1, sigma 2, sigma 2, sigma 3. Sigma 2 square is equal to 1. So that will be sigma 1, sigma 3. But then when I take a trace over sigma 1 or over sigma 3, that will give me 0. And there is no term that occurs here in this expansion that will not be 0 when you do this sum. Because you can easily convince yourself. Take this, take all of the tangents. Then you will left with 1 sigma 1 at the left hand and sigma n on the right. Because all the other ones come twice. So they will sigma square is equal to 1. So in that case again, all these terms, when you take the trace, it will be 0. The only term that will survive is where you don't have any of these tangents. And that's this one term. Take 1 from each of these things. And then when you take the trace, each sigma can have 2 values. So it is cosine hyperbolic beta j raised to the power n minus 1 and then 2 raised to the power n. Why 2 to the power n? Because each sigma can have 2 values. And of course, just summing this 1. So whatever value of sigma doesn't matter. For all of them it is equal to 1. So you have 2 to the number of spins that you have in the system. So this is the simplest calculation that one can do for the rising model on line with free boundary conditions, where as I've just done here, you can explicitly calculate the partition function, and if you know the partition function, then from that you calculate the free energy, and from that specific heat, etc., etc. All these things can be calculated for this thing.
Maybe can you again tell the reason why it is 2 to the power n?
Oh, so we are doing this. Sigma 1 equals plus minus 1, sigma 2 equals plus minus 1, like that for 10 spins. And term that is surviving is just 1. It doesn't depend on sigma 1 or sigma n. So for each value that I choose for sigma 1, it is 1. For each value I choose for sigma 2, it is 1. And we have sum over all these possible configurations. The number of possible configurations is 2 raised to the power n, because each of these variables can exist in 2 different states. So this tells you about the partition function of n eigenspins on a straight line with 3 boundary conditions. That here sigma n appears by itself, sigma 1 appears by itself, So when you take a trace, then say give you 0. All the branch functions, any term that you get in this expansion which involves one of these branch functions will have some free spins, some spins which occur only once. And when you take a trace, then that will be used. So what does it tell me? So when I have this expression, explicit expression for the partition function, then I can calculate the spin energy minus k t log of z. And from that, take a derivative with respect to the temperature, that will give you the entropy. Take two derivatives, that will give you the heat capacity and things like that. So, but this is a perfectly well-behaved function as a function of temperature. And basically, whenever I take derivatives and things like that, I don't get any singularity anywhere. This is a smooth function of temperature, and you can actually write down, for example, expressions for the specific heat and plot it as a function of temperature, all that. You'll see that it's just all the way down to t equals 0. It's a smooth function. There is no singularity anywhere. And you also know that if there are phase transitions, then one expects singularities. So this just tells you that this model doesn't exhibit any phase transition. It doesn't exhibit any phase transition in the sense that, it's always paramagnetic. The average magnetization is always equal to 0. And however low a temperature you go to, then it remains 0. And all the other physical properties like internal energy, specific heat, etc., are very smooth functions of temperature, and there is no point where things show singularity here, etc. So this automatically tells you, although I have not really got there, I have not told you about the singular behavior of various quantities near phase transitions, but this you know from thermal courses that for example, whenever there is a phase transition, there could be a discontinuity or there could be some divergence of some quantities. So that doesn't happen in this system. So this means that there is no So this is of course a little not all that interesting. I mean, one would like to study phase transitions and so on, but you also know that when there is a phase transition, it becomes very difficult to actually do a theoretical analysis of that. The fact that you can calculate everything explicitly here, that in some sense goes with the statement that there is no phase transition, because if there were phase transitions, then we would not be able to generally calculate everything explicitly. So that's one thing. We'll come back to that later. I just want to also point out one more thing, which is basically some general thing. Here, the boundary condition that we have used is a free boundary condition. That there is nothing on this side, there is nothing on that side. But you have heard about other boundary conditions, right? I mean, when you study problems involving electrons or whatever. What kind of boundary condition are you familiar with? What other kind of boundary condition are you familiar with? People at the back? Not instances. Who has heard about periodic boundary conditions? People? Yeah? So what does it mean? Basically means that this thing gets repeated on that side. Or, I mean, what says is that this last one, there is coupling, and that coupling also is equal to J. There is a term in the Hamiltonian, in addition to this, there will be a term which is J times sigma 1. Yes? Now, what difference does it make? I mean, if I now include this term, then how would this partition function change? Any idea? So I have to there is eventually a term which is sigma n. There is n minus 1 n term there, and then there is a sigma n sigma 1. That's this one. And there will be a n here. This number of bonds is equal to now the number of sides. So if I now do the trace, then my claim is that there will be another term which will give you a non-zero value. Which is that term? Yeah, so when you take this from every bracket, so there will be sigma 1, sigma 2, sigma 3, sigma 2 squared will give you what? Give you sigma 1, sigma 3, then sigma 1, sigma 4 all the way. And eventually there is sigma 1 left here, right? And that sigma 1 will go into this sigma 1. So if you take the stands for all of these terms within the brackets, that again gives you something which is constant, it doesn't involve any of the sigmas. So that will also give you non-zero trace. So what is that term? So there was a term which is 1, but I am taking 1 from every one of this pairs, and then there is a term where I take this hyperbolic tangent from each of these pairs, which is tan beta j raised to the power right? And these are just numbers, so when you take the trace, they will get 2 raised to the power n. So now with periodic boundary condition, there is an extra term here. But for large n, what is the value of this quantity? Hyperbolic tangent of some positive number. Is it something which is bigger than 1, smaller than 1? Can't tell.
Maximum value is 1. So
Maximum value is 1. When the argument becomes close to infinity, then it goes to 1. Right? So this quantity for any value, finite value of temperature, this quantity is some value, some number. But it has to be less than 1. And when you take a number which is less than 1 and raise it to the power n, and n is large, what do you get? It goes to 0, right? So in the large system size limit, when this n becomes very large, this term will go to 0 in the large n limit. So whether you have this term or not, it doesn't matter. So I mean, this goes to show that large system, if you have short-range interactions and so on and so forth, boundary condition is not all that important. You do your calculation using a boundary condition which is convenient for you. So basically, either case, with periodic boundary condition or with free boundary conditions, you get this cosine hyperbolic is to the power n or n minus 1. Again, for large n, it doesn't matter whether you have 1 n or 1 minus 1. So the conclusion that one has that this is a smooth function of temperature, and all the thermodynamic quantities also will be smooth functions of the temperature. That doesn't depend on whether you're using free boundary conditions or periodic boundary conditions. And the conclusion that there is no phase transition, that remains. Right? So if you don't follow what is going on here, then later on we'll find it much more difficult to follow, because this is the simplest example where we are looking at an interacting problem for which one can solve everything explicitly. Okay, so I assume that this is not a difficult thing, and you are more or less following what is going on. One thing that this conclusion that I have just drawn, that there is no phase transition, there are that just follows from doing the calculation, doing the actual calculation of thermodynamic quantities and showing that there is no singularity here at any finite temperature. But then one can understand, try to understand why is it that in this model there is no phase transition. There is this tendency of the spins to line up, that is there, right? Hamiltonian already says that. Hamiltonian says that when these two things are parallel to each other, then the rate is less. When they are anti-parallel, the rate is more. So they would like to be parallel to each other. But now this exact result is telling us that yes, there is a tendency for the spins to line up, but that does not lead to a finite magnetization. Finite fraction of the spins pointing in the same direction, that does not happen. So why does it not happen in one dimension? That happens in other dimensions. You know that Ising model in 2 dimensions. One of the nice things about the Ising model is that it has been solved exactly. There is famous work by Lars Sagar, who actually was able to solve this Ising model exactly or square lines. And that solution does show that there is a critical point such that if temperature is higher than the critical temperature, magnetization is equal to 0. If temperature goes below, then there is non-zero magnetization, and there are all sorts of singular behavior, specific heat, susceptibility, all those things at the transition point. And one can calculate the singular behavior explicitly. So that's a very, very important result. But the point is, in 2 dimensions, one knows that the same model has a phase transition. But in 1 dimension, one is finding that from this calculation that there is no phase transition. So one has to understand why in 2D there is phase transition and in 1D no phase transition. So let me just spend a little bit of time on that, because that's instructive. That
Sir,
yes,
use this board now, sir.
which one?
This one.
Just this one. So then I have to engage that, so that's okay.
Ah,
Right? You have more of the circle.
yes, sir.
This picture. So again, this one-dimensional Ising model. You have this lattice types, and there are the spins which can point, which can take +1 value or -1 value. +1 value, pictorial representation. +1 value I will represent by up arrow, and -1 value I will represent by down. So a particular configuration will be putting in this up arrows or down arrows on this lattice types. That will, depending on how many up arrows and how many down arrows you have, there will be some magnetization, which is just the difference between the number of up arrows, number of down arrows. And what we would like to find out is that at any finite temperature, whether it is possible to have a situation where there is a finite magnetization. The macroscopic fraction of the particles will be either in the up state, and the smaller number will be in the down state, and so on. To sort of address this question, there is sort of a general framework from which one can sort of try to understand this. One starts with basically the ground state of the system. Zero temperature system will be in the state with the lowest energy. So what is the state with the lowest energy? Yes? How many such states are there? 2 such states are there, because all of them can be up pointing and all of them can be down pointing. This is the symmetry of the problem. This another thing that is important is that if I look at the Hamiltonian, the energy is invariant under a reversal of the spins of all the particles. So, I mean, this is important to keep in mind. That if I now do this global spin thing, sigma I goes to minus sigma I. This is a global operation where I'm taking the spins of all the lattice sites. And since it is quadratic in the spin variables, when I make all of them minus, energy doesn't change. So the symmetry of this Hamiltonian is that it's invariant under a global spin field. That will change the signs of all the spins, but that energy doesn't change. So if we have a ground state, it has to be doubly degenerate. Because whatever ground state you say, if we flip all the spins, then again it will remain a ground state. And that you can easily see that, all of them are plus 1, all of them are minus 1, they have the same energy. So we start with the ground state. I don't know how many errors are going to draw. This is one of the ground states. And what is the energy of this ground state? Eg minus J times n minus 1. Because there are n minus 1 bonds, and each of the bonds is contributing to minus J here. So, right. So the question is, if I go to finite temperature, why doesn't some vestige of this state remain? In the sense that this is a magnetized spin, this is fully magnetized. Magnetized spin is equal to n. Every spin is pointing in the same direction. That is to ground state. Now, if I go to finite temperature, the calculation that I have done earlier tells me that something happens, and this nice arrangement of all the spins where everything is pointing in the same direction gets totally changed. That it doesn't have any concept of magnetization anymore. So why does that? So to understand that, you basically have to look at now at finite temperature. Just the ground state is not enough. Right? Finite temperature basically says that there will be corresponding waves to excited states. The question is, what are the excited states of this problem? Can you suggest some excited state? I mean, whose energy is slightly higher than this ground state?
Half of flip
Any spin flip that is not good, because then the two bonds are broken. So, but wait, if I now, so yeah, it's just a good idea to sort of think about this. If I do this, right? So then there is a plus minus in this bond, plus minus in that bond. So this energy is bigger than this by 2 times J, or not 4 times J. Why 4 times J? Because it was minus J to begin with, and then it's become plus J. So there is a 2J energy for each broken bond, and now there are 2 broken bonds, so there will be 4J. That's one of the excited states, but it is not the lowest excited. So what is the lowest excited?
Halfway through, they are up, and then in the middle, everything goes down.
Does it have to be halfway through?
Not necessarily.
So yeah, it's just that, part of the system is up, part of the system is down. So if I now look at this state, where now you have down on all of these sides. So again, all these bonds are ferromagnetic. All these bonds, the 2 spins are parallel to each other. So they will give you minus J. Similarly, all these bonds will again give you minus J because the spins are parallel. But there is one bond here which is 1 spin up and 1 spin down, that will give me plus J. So the energy of this state is Eg plus 2J. Somebody said the spins at the ends. That also works. Spins at the end basically means that, but this is exactly the same cause of this. So whenever this happens, what I do is I put a line here. I say that on this side everything is aligned in the up direction, on this side everything is aligned in the down direction. And this line is called a domain bond. separates two ordered states. And this domain one concept again is very important in magnetism. I mean, if you have three-dimensional magnets, whatever, there could be such domain walls, domain boundaries, which will separate one ordered state from other equivalent ordered state, related to it by symmetry. But here the domain wall is just a line of up spins. Domain wall separates a line of up spins from again a segment where everything is down. And this energy is some 2 times. If you flip this one, then the domain wall will be just there. So this is just a special case. Flipping the boundary is basically putting the domain wall at the last one. And that also gives you 2J. So basically, there are how many such excited states are there? Yeah, so there are n-1 bonds, and you can put the domain wall at the middle of any one. So you have a excited state, set of excited states. Excitation energy is finite, it's just 2J. But there are many different ways in which you can create this excitation. So thermodynamics, what does one do? One looks at not just the energy, not just the entropy, but some combination of energy and entropy. In this case, it's the Helmholtz free energy. So one has to look at some free energy, which is E minus T times entropy. So, I mean, as I'm going from the ground state to this set of excited states, energy is going up by 2J. Delta F, delta E minus T times delta S. Delta E is equal to, this is equal to 2J. All this manifold of states where you have a domain one has extra energy 2J. So increase the energy by 2J. But what is this delta S? The entropy of the ground state is, you can call it, if you just consider one of these ground states, it's 0, otherwise it's log 2 or something. But the entropy of this manifold of excited states is going to be what? Because there are n-1 different such states, which is of the same energy, but it's a multiplicity of n-1. So entropy is basically kb times log of number of states with that particular energy. So this is minus T times kb times log n-1. So going from the ground state to the first excited state, the change in the free energy is this one. 2J is coming from the change in energy, and this log n-1 is coming from the multiplicity of this first excited state. Now we are always, of course, looking at very large values of n. So what the small value of t is, this term multiplied by log n will always be bigger than, and one can always go to temperature which is low enough, for which this term is going to dominate over that. So by creating these excitations, you are actually lowering the free energy. So the state where these excitations are there is going to be favored over the ground state. And these excitations basically make the magnetization 0, right? I can put this domain wall anywhere. And then if you look at the manifold of states where there is a domain wall, and then I try to find out if the spin's average is 0 or not 0, we'll find out the spin average is equal to 0. Because this domain wall can be anywhere. And whenever you move the domain wall, you basically flip the spins on this side. And so if we average over all such configurations, we will find out that the magnetization at any finite temperature is going to be equal to 0 in the large n limit. This large n limit is important because if you have some finite n, then one can go to a temperature which is low enough such that this quantity remains positive. So in finite n, we will see a finite magnetization at low enough temperatures. But as you go to big enough systems, thermodynamic limit where n goes to infinity, then there is no finite temperature at which this one-dimensional model will show finite magnetization. And so, I mean, this argument is known as Spiral's argument. it can be generalized to other spin systems, etc. But this is something that again is important, because if you want to look at the possibility of having an ordered state, then you have to look at excitations. And you have to look at whether the excitations basically are sufficient to kill the order, or in spite of excitations there will be some order. So, and this argument can be generalized to continuous spins to higher dimensions, situations like that. So, this is clear? Everybody understands this? And this is one of the basic things in trying to figure out whether order is possible or not. And here, 1D, there is order is not possible, because these excitations are domain walls. They cost finite energy, but they have their entropy contribution diverges in the thermodynamic limit. So the entropy part always overwhelms the energy part, and will produce these domain walls spontaneously at any finite temperature.
Just a question. Supposing I have something where you just put one spin in device. Supposing I put lots of them, so I get the square wave analog of the spin wave. That will be presumably in this case higher.
Yeah. So it's actually instructive to think in terms of this domain walls, because every spin configuration can be thought of as a configuration of the domain walls. Whenever I have up spins and then some down spins and some up spins, whenever the up goes to down, they put a domain wall. And so there is a one-to-one correspondence between this kind of configurations that we are drawing on the lattice and the configuration of domain walls. And so you can formulate the problem essentially as one of this domain walls. There is a finite amount of energy for each domain wall. So if you have 5 domain walls, then there will be 10 J energy that is. But there will be many such configurations, etc. So what do the same kind of calculation entirely in terms of the domain walls and show the same result. There will be always qualification of domain walls. So before I go on to something else, what do you think about 2 dimensions? I mean, if you want to do an argument like that, then what would be different in 2 dimensions, which will make it possible now to have order? All the spins are not parallel. You see, in the excited state, these 2 spins are not parallel. Spins on
there
this.
any possibilities that even in excited state, all these spins are aligned in only one direction?
There is not unexcited state. That's the ground state. No? In the ground state, where all the spins are in the same direction, that is the lowest energy state. That is the ground state. So we are looking at states which have energy higher than the ground state. Those are the excited states. And so there, some pairs of spins will not be parallel. If all of them are parallel, then the energy is the same as the constant. Here, as you can see here, this is the first excited state. All the spins on this side are parallel. So you'll get the same sort of minus j from each of these. Similarly, here also, all of this will give you minus j. But there is this thing in between, where one is up and one is down. And this is, of course, not parallel. So that will give you a positive energy. So that will be an energy which is higher than that of the ground state. And that's the first excited state. Energy is ground state energy plus 2J. So if we want to carry this argument over to 2 dimensions, then why does it go wrong in some sense? Why this argument doesn't work anymore? So yeah, it's not so difficult in the sense that I'm not going to go through the whole argument, but I'll just draw a picture which will be like a domain wall but with two dimensions. So if I want to draw a domain wall, this is what domain wall means. It basically means all spins on this side are up, all spins on this side are down. But the energy of this domain wall, see, earlier there was only one row of spins. So the energy, extra energy was just 2J. But if I want to divide a two-dimensional lattice into one region where everything is up and one region where everything is down, then this side, the length of this side of the lattice, that comes into the picture. So there, a simple straight domain wall, the energy is delta E, 2 times J times the length of the system. And again, when you go to thermodynamic limit, this energy is going to diverge. So this kind of a domain wall, not so easy to produce in 2 dimensions. And if you then compare with entropy, the entropy calculation becomes more difficult because this domain wall can basically fluctuate. So we have to look at basically these fluctuations in the domain wall and how many different places you can put the domain wall and so on. But again, one can do this calculation at least approximately, and one can show that below a certain temperature is the energy part which wins out, above a certain temperature is the entropy part that wins out, and that temperature is basically when you go from the order to the disorder phase. Then you go 0 to 1 -1.
So in 2D there is one domain wall which extends throughout the system as you were showing. But there is also a domain wall that is possible which is like a closed loop.
Yeah.
So how can one explain that?
There also the length of the domain wall will be possible. So when you have a loop, the loop can basically get rid of the order only when its size is comparable with the system size. Right? The number of up spins and number of down spins have to be comparable. So there again the total length of the domain wall
Again, the
will be
energy
proportional
wins
to.
over length.
Yes.
I had a question in the 1D case. So the argument for zero magnetization basically was that the entropy term dominates. So if we see we saw it from the perspective of going from the ground state to the first excited state. But zero magnetization corresponds to the state where everything is anti-parallel basically, right?
No. So I mean, this state also has zero magnetization. This state, domain wall sitting at the middle. Then again magnetization is equal to 0.
Okay.
So it doesn't mean that every spin is anti-parallel. Every pair is anti-parallel. That will happen at very high infinite temperature.
Yeah.
But any low temperature near T equals 0, these are the kind of exceptions that we'll see. That there is a large part of the chain where everything is lined up. The remaining part of the chain, things are pointing in the opposite direction.
So then zero magnetization means it should be at the halfway point.
No, this wall can move. So I mean, if the wall is here, then we'll say that there is more negative than positive. But if the wall is there, then there is less negative and more positive.
Also average out.
Yeah, so in all possible positions of the wall have to be taken into account. Yeah? And this is actually what you asked actually is very important. This is going to be my next topic. I'll go on till another 15 minutes. Yeah? So the point is there is no long range order. That doesn't mean that there is no short range order. So there will be actually in this model, we'll see that there is short range order and then there is a coordination length, and the length will become very, very large at low temperatures. So whenever you're talking about this kind of magnetic systems, order disorder is one quantity. That's just the order parameter. Magnetization is 0 or non-zero. But there are many states with zero magnetization. There are many states with non-zero magnetization. And these states, thermodynamic states, are different. And they differ because one of the reasons is that they differ because the degree of short range orders, degree of correlations in those states can be very different. So I just want to define this new quantity which I have not done so far, with just dealing with thermodynamic quantities. Yes.
Sorry, just follow up on what I was saying earlier. So consider a domain in which like all the spins are up except for one spin. Okay. Then the delta E is what, 8J or something.
Yeah.
And the delta S, because there are L square, L square.
You will have those excitations.
Yeah, so then
Those
entropy
excitations
would dominate.
No, but those excitations do not give you a M equals 0 state. You still have n minus 1 spins which are up and just 1 spin which are down. So we average of all of them, then we get n which is like 1. So the question is not just excitations. There will be excitations always. I mean, 3 dimensions, 2 dimensions, low temperatures, there are excitations. The question is whether these excitations are sufficient to kill the order or not. So to kill the order, you have to have a macroscopic fraction of the spins in the down state. The frequency and the radius of the orbit, everything you know. So depending on where the orbit starts, there will be different kinds of skipping orbits. And you have to take into account all of them. And
so if we sum of all of them,
yeah. Okay, so now we go to the quantum problem. The quantum problem, as I said, this was worked out by Landau, and who showed that there is indeed a diamagnetic response. So what is now different between this and the quantum treatment that Landau worked out? So how many people actually have seen of charge particle in a magnetic field? And you saw it just now. I mean, he wrote down the Hamiltonian. So the question is, what kind of solution you get out of that? Not many, huh? So I will just write down the same thing, but I'll just use a different gauge as compared to what he did. That makes calculation simpler. There was a question, why choose that particular value? Symmetric gauge, and here what I am going to do is basically what is known as the Landau gauge. So the Hamiltonian is P operator minus some and I see that this is old fashioned. I mean the C doesn't appear in any book anywhere. So I mean when you do what is it called, SI units, some 4 pi, etc., etc., but whatever it is. This is the Hamiltonian associated with the motion of the electrons. I am not putting in the spin part. Spin part we have already taken care of. That part is separate from what happens as the orbital part is concerned. And E you can take to be negative. I mean, this is always again another thing that I get a little bothered about. Electron charge is actually negative, so this E is a positive quantity or a negative quantity. But nothing matters. Nothing depends on that. Now, basically, now we have to choose a gauge, and the gauge that I choose is AX. H unit vector in the Z direction. So del cross A will again give you Z direction. So what we have here is Px minus H times y mod squared well, I mean this should be actually all vectors. There is no vector anymore. This should be plus E by C. Right, so this should be clear to everybody. So this, I mean, the values of this. That is the problem, and really sort of a part and a part that looks like a harmonic oscillator, and those harmonic oscillator part is called as Landau levels. How do you get that? I will not do the whole calculation, but I will just write down the steps, which is fairly simple. By the way, what Stansid was saying, formally you can say that you can call this px prime, py equals py prime, pz equals pz prime. Just change your variables, and then you just get p squared over 2m. So the classical thing it says that it doesn't matter. You get the same partition function irrespective of what the value of b is, and you get basically no magnetic response. But now quantum mechanics you cannot do that because you have operators and they don't commute and so on and so forth. But this simple, no? I mean, if I want to sort of diagonalize this separately, so this I will have some write down the kzz. For these two, I'm just writing down some wave functions. It will be kxy, call it kx, and then some kz over from this part we'll just do the plane wave part. And this kx and ky, kx and kz, if you have periodic boundary conditions, there you can find out what kind of values they should have, and so on and so forth. And when you put that back in here, then you will see something that looks like a harmonic oscillator. In the sense that sorry, not this made the wrong mistake here. This should be x. So some function of y. Right. So this is I'm writing my wave function like that. Wave function, something like that. So kzz, if you just do this, you will just get kz squared over 2m, h cos squared kz squared over 2m. Whatever happened to IH word. Kx times x, if you look at this, then this will give you what? This will give me some kx, something multiply kx. Kx plus some y mod squared. And then there is py squared. Right? So that looks like a harmonic oscillator which has been displaced not from y, not at y equals 0, but some value of y. Yeah? So I mean this then looks like y minus y naught squared, and then there is a multiplied by something, and then there is a py squared over 2m sitting there. These two gives you a one-dimensional harmonic oscillator. And basically, so then you have this quantized energy levels, n plus a half h bar omega 0. So there will be kz squared over 2m coming from here. Py squared plus this combined gives you the harmonic oscillators. So the energy spectrum of this looks like epsilon, we have to now have a quantum number n associated with the harmonic oscillator part, and then there is a kz here. Kz. Omega c is the cyclotron frequency. So you can just two lines of algebra which I have not written down here, but it's fairly easy to do. Pz squared is trivial. I mean, it just gives you h squared kz squared over 2m. Py squared I keep as such, and then px operating on this will bring out some kx, something multiplied by kx, and then you will have this y minus y0, call that y0, y minus y0 squared multiplied by something here for this term, and then combining that with this term gives you just a harmonic oscillator Hamiltonian. And if you do it correctly, then the frequency of the harmonic oscillator will be EH divided by MC. So this is the difference now between the classical treatment and the quantum treatment. Classical treatment, of course, there was no quantization, nothing like that. Energy was independent of the magnetic field. That's what we argued. So free energy doesn't depend on the magnetic field. But here, the spectrum has changed. Spectrum has changed, that there is a continuous part of the spectrum, and then there is a discrete part of the spectrum, and these discrete energy levels are called Landau levels. And if I want to do now statistical mechanics of that, then I have to take into account the fact that we are dealing with this kind of a complicated energy spectrum. And I have to do the calculation using the Fermi statistics. I have to again, these are the single particle energy levels, so I have to fill out the single particle energy levels up to a certain, so that all the number of electrons can be accommodated there. So that calculation is not a trivial calculation, because it's the density of states, you get a continuous function from here, but then there are discrete steps there. So there is one Landau level when this kz equal to 0. So I mean, you have this. These are just these discrete levels, but then with this level I have not taken into account this kz. So there will be density of states above that also. And similarly, each of these discrete levels will then get patterned. Yeah.
So we see that the harmonic oscillator thing, Hamiltonian, comes when we have the quadratic potential. But here, how did we get this? I'm surprised that without any boundary condition we get this. The harmonic oscillator.
The potential is of this form, no? I mean, this is simple. This, if I had done, instead of this gauge, if I had done other symmetric gauge, then you would see something that sort of more looks like a cyclotron orbit. But in this gauge, after just a few lines of algebra, we will end up with something that looks like harmonic oscillator as far as Py part is concerned. And from that, if you want to calculate it is, you will see again the cyclotron orbits. Get the wave function for the harmonic oscillator.
So these energy levels are something that we can observe.
Yes.
Right? But then it shouldn't matter which gauge I choose. I should still have the same
Right.
energy
So
level.
energy levels doesn't depend on, but the kind of physical picture that you have in mind is what we had done in the previous picture, that the electron goes around in the cyclotron orbits. But here it sort of looks like that it is more like a harmonic oscillator. So it's actually the wave function that we are talking about, And wave function, in some sense, will the actual form of that will depend on how you do the calculation.
Yeah, no, so the point is that the spectrum is exactly the same, but there's a huge degeneracy.
Yeah.
I mean, the degeneracy is proportional to the macroscopic area. Therefore, you can take any linear combination of those degenerate wave functions and therefore form something which looks completely different, orbits. So that's the way it happens.
So this we didn't talk about, but the point is, you see, this Y0. Y0 is basically the harmonic oscillator minimum potential, right? Y0 involves this Kx, because where does it Y0 come from? This comes from this Px operating on e to the ikx. And the Kx I can choose, how many, when you have periodic boundary conditions, you can just Kx you choose to be, depends on, how big your system is. So there is a spacing between these Kx values. It's 2 pi over Lx. So you can choose this many Kx's, but all the Kx's will give you the, basically the same. I mean, it doesn't matter. Energy of harmonic oscillator doesn't depend on what is Y0 is, where you center it. So huge, each Landau is actually
Sir, what variation we can see in energy level if the magnetic field is depend on time? What variation we can see on energy levels if the magnetic field is depend on time, if it is changing with time?
Again, depends on, then you have to do time-dependent quantum mechanics, basically. I mean, here we are doing, saying that the Hamiltonian doesn't depend on time. But if the time dependence is slow, then you can solve the Hamiltonian for some value of the magnetic field and then some other value of the magnetic field. And if this process is very slow, then you will see the changes in the Landau levels.
Could you comment on if I put a current drive, do I get the classical Hall effect with these? I mean, do I get a Hall effect like behavior in these two?
I think yes. I mean, this Landau levels have become very, very popular when this quantum Hall effect was discussed. So all those can be sort of understood from here.
As you mentioned that Kx is a cyclic coordinate here in the energy levels, basically. So we know that whenever there is a degeneracy, there is an operator that commutes with the Hamiltonian. So can you show which operator commutes with the, can you show the symmetry here?
So this obviously it depends on y. So it under translation in y, it doesn't, it's no longer invariant. But, for example, in the z direction, there is translation in the z direction which is symmetric.
Oh. Okay, there is a X translation symmetry. Okay.
But I don't know what this degeneracy you're talking about. I'm not quite sure whether that comes from that symmetry or not. That's something that one has to. You're saying that since this energy levels.
I think X is not present in the Hamiltonian, so it's invariant under X translations. But that's artifact of the gauge choice.
Yeah.
So can one, in general, show?
Not sure. I mean, what symmetry that would give you this degeneracy of the Landau levels? Something that not clear to me. I mean, this gauge, I see that this translation involves only y here. So the other two directions are free in some sense. So that will give you some loss of symmetry operations. But
in general,
area, So so I'll just wrap up quickly. So this is the formulation of the problem. write down, for example, what, just use Fermi statistics and then fill this levels up to a Fermi level, and then look at the energy and how it depends on. Energy now depends on magnetic field through this. Omega C now depends on. So that calculation, which involves a partial sum and a partial integration, is not trivial. I am not going to do it here, which is worked out in many standard, actually not even worked out in standard books, because it's a fairly complicated calculation. But you see where we are going, in the sense that, we have calculated the single particle energy levels, and we are dealing with a system of fermions, where you have single particle energy levels. So you fill up the single particle energy levels up to a point such that all the states that you have filled, number of electrons that you have put on those states is equal to the actual number of electrons that you have in the system. And that will change, because now as you change H, then these things are going to move up and down. Landau levels are going to move up and down. Landau levels sometimes will go through the Fermi energy, sometimes the Fermi energies lie in a system where it is far away from the Landau level, etc., etc. So all these complications are there. And from that, eventually, as we had done in the case of Pauli paramagnetism, you will get some energy, free energy that will depend on H. From that you get the magnetization by differentiating with respect to H, and get a susceptibility. So once one has done all of that, one finds the final result that if you do the calculation properly, taking into account the discreteness of the energy levels, that is the important thing. Now you see, in many cases, for example, when you're doing ideal Fermi gas and things like that, although you have to sum over k, for example, you convert that to an integral. But that you cannot do. If you do that, then you will get back the whole result, that there is no response. So the actual sum that is there, the fact that you are doing quantum mechanics and the levels are discrete and you have to do an actual sum, not so much an integral, or convert that to an integral, then you don't get anything that is interesting. But if you do it properly, then one finds the following result, which I'll write down, and then that will be the end of the lecture today. So the susceptibility, zero field susceptibility that you do when you do this, and also of course you have eventually to add plus the spin part, because we are talking about the energy of an electron, which will have this orbital part coming from here, and also the spin part coming from the spin angular momentum. So then you get chi equals 1 over volume density of states at the Fermi surface, the mu v squared. This should look familiar, because exactly this is something that we got for the Pauli. But now you will get 1, which is the spin part, and you will get, this is the diamagnetic part, which is coming from this calculation, taken into account the discreteness of the Landau levels and doing the sums properly. And you will get basically overall still paramagnetic, but the total susceptibility is not what you would get simply from the Pauli calculation, but it will be reduced by 1/3 coming from this Landau calculation. So overall, I mean, still expects the system to behave paramagnetically, but there is a catch. Just give me 2 minutes, I will just mention that. The catch basically that the mass that come in here and the mass that goes, for example, in the mu b need not be the same, because mu b, the spin part, is an intrinsic property of the electron, and there the true electron mass comes into the picture. But here, when I write this Hamiltonian, this looks like a free particle Hamiltonian, but if I'm talking about electrons in a metal, then there are not be, actually can be quite very different from the bare mass of a free electron. And that mass comes in this calculation. But it doesn't come in the Pauli part. Pauli part deals with spins, where the Bohr magneton doesn't care whether you have band structure or not. So basically, if I do that, then what happens is this. This 1/3 gets replaced by m over m star. Yeah. I'm putting this here. So when I write the orbital part, then I put in effective mass, not the free electron mass. Then all these things go through, but there is this 1 over m star squared sitting here that comes in here. And so basically the issue is this, that this m star, whether it's bigger, smaller, whatever it is. So you see that this m star is this 1/3. M star is like, m by 2. Then you see that the whole thing. According to the Landau calculation, although overall response of free electron gas should be paramagnetic, there is a diamagnetic component, but it is smaller than the paramagnetic one, the Pauli part. But for a band system, for a real electrons in a metal, because of this effective mass effects, the whole response can actually be diamagnetic. So I think this is sort of instructive in the sense that says that in both cases we are looking at, when you're looking at this first theory of paramagnetism, we are looking at isolated, localized spins, but here we are looking at spins which are moving around, so they have the orbital part as well as the spin part, and they're all in the same volume. The actual statistics is important. That can make a whole lot of difference. The magnetic response can be totally different depending on what kind of physics you are looking at. So I will kind of stop here. I think next time onwards. So far, we have not done anything with interactions. We're still doing single particle problems. But there are also talking about some interactive systems. How to deal with that.
Thank you, Chandan. Questions? Okay, you can maybe discuss with Chandan later. So thanks, and I guess this ends this.